negative deviation. Now let us see non-ideal solutions with negative deviations. Now the solutions in which the intermolecular forces between solute and the solvent are found to be stronger than what they were having individually between solvent-solvent, solute-solute molecules are actually called the non-ideal solutions with negative deviations. I'm repeating again. What happens in these solutions is the intermolecular forces between solute and solvent are found to be stronger. They become stronger than they used to be in their individual cases. Like, we can take the example of the mixing up of nitric acid with water. What we find is this nitric acid is actually able to form hydrogen bonding with water molecules from these different sides like this. So it is able to form hydrogen bonding from this hydrogen, from this oxygen as well as from this oxygen. So more extensive hydrogen bonding is formed between nitric acid and water molecules. Due to this extensive and stronger bonding between these two species, what we find is the rate with which they used to evaporate individually in the solution gets lowered. And what we find is therefore lesser number of molecules of both A and B will be present in the vapor phase. And that is why the partial pressure of both these components were found to be lesser than what it used to be as per the Raoult's law value. Therefore, we can write that the PA will be lesser than what it used to be or it can be from the product of P naught A and XA. See, this is the value which we get from the Raoult's law, and PA is the partial pressure of the A. So experimentally it was found that the PA is less than the what it used to be from the Raoult's law value. Similarly, the PB will be less than P naught B XB. Why? Again, because the forces are now in this case stronger. They are much more stronger than it used to be in their pure state. So in these solutions, what we find is net volume of the solution gets decreased. This value is negative. Molecules are coming more closer to each other. Decrease in the volume of the solution takes place. So if you are mixing 50 ml of nitric acid with 50 ml of water, don't expect the volume to be 100 ml. It will be less than 100 ml. It will be somehow 98 or 97 ml. Because molecules are coming more closer to each other. That's why this value is negative. Also, what you need to understand is since much stronger forces are formed between solute and solvent molecules than it used to be in the previous cases of the original solute, and solvent, the enthalpy of the solution is also negative because more amount of energy is released than it was consumed in the breaking of the original solute and solvent molecular forces. So enthalpy of the solution is negative. We can have many other examples of this type, like we can have example of mixing up of sulfuric acid with water. We have taken nitric acid with water. We can have the example of mixing up of phenol and aniline, and we can also have the example of mixing up of acetone and chloroform. We were expecting dipole-dipole interaction in both these cases, but what we find is that this acetone develops hydrogen bonding with the hydrogen of the chloroform molecule because this hydrogen becomes highly electron deficient due to the presence of 3 electronegative chlorine atoms. As a result, it develops hydrogen bonding with the oxygen of the acetone. So these all are the examples of the negative deviations. Let us see now the px diagram of the negative deviation solutions. Now these dotted lines are the ones which are showing the behavior as per the Raoult's law. See, we have taken the same px diagram. X-axis is having a mole fraction, y-axis is having the vapor pressure. This side, left side is for the pure solvent. Its mole fraction is taken as 1, whereas the mole fraction of the solute is 0. Right side is for the pure solute. Mole fraction of solvent is 0. Mole fraction of the solute is 1. This is the vapor pressure of the solute in the pure state, and this is the vapor pressure of the solvent in the pure state. So these dotted lines are the ones which are showing the behavior, actual behavior we were expecting as per the Royd's law. But experimentally what we get is that the vapor pressure of the solution was found to be far less than this dotted line. Why? Because the forces between A and B are now in this case are stronger. So the graph is following this line, this graph, this path, this, and the values are less than the expected values. So it's called the graph for the negative deviation. And along in this graph of the solution, which is the PS1 is, there lies a point where the vapor pressure of the solution is minimum. When vapor pressure is minimum, you can find out that the boiling point will be maximum. That's why it's called maximum boiling azeotrope. And we can find out that we can clearly see here that both these the graphs of the individual components are also actually lying below this usual value because they are also showing the negative deviation. So this is the graph of the solutions which are showing negative deviation, and the example which we have taken of the nitric acid and water, from here, from this point we can drop a perpendicular and we can find out what exactly is the composition of the solution at this point, which is the maximum boiling azeotrope. We find that whenever the water and nitric acid are mixed, at maximum boiling azeotrope, nitric acid is found to be 68% and water is found to be 32%, and the solution boils at 393.5 Kelvin, which is actually more than the boiling points of both these liquids. So this is what is your are the examples of the liquid solutions which are non-ideal and are showing negative deviation.